In this video, we're going to talk about the fixed field of a group of automorphisms. So in this table here, I've just represented all four of the automorphisms that we found in the previous video of the extension field Q adjoin root 2 and root 3. Let me write that down. So these are automorphisms of Q adjoin root 2 and root 3 over the rationals. Okay, those are the four automorphisms there, and I've just recorded what they do to each of the basis elements for this extension field over the rationals. Anyway, our purpose in this video is going to be to take a couple of subgroups of this group of automorphisms. We know that automorphisms form a group because composing any two of them gives us an automorphism, and the inverse of any automorphism is an automorphism. So take a subgroup of this group of automorphisms here and figure out what is the set of elements of Q adjoin root 2 and root 3 that are fixed by that subgroup. All right, so first of all, just a reminder, if phi is an automorphism of an extension field of F, if that's an automorphism, then the set of all x in K such that phi of x is equal to x, that is, the set of all elements that are fixed by phi, is a field. We've proven that before. Okay, and a corollary of that is that if we have a subgroup of a group of automorphisms, so if G is the group of automorphisms of K, and H is a subgroup of G, then the set of all elements of K such that phi of x is equal to x for every phi in H, so for every phi in the subgroup, that's also a field. And the reason that's also a field is because it's going to be an intersection of several fields. It's going to be an intersection of this field for every automorphism in our group, and the intersection of a bunch of fields is a field. Okay, so our job in this video is to pick a couple of subgroups just for exploratory purposes and figure out what their fixed fields will be. All right, so just as a reminder, this group here is isomorphic to Z2 plus Z2. We know it's a group of order 4. We know that groups of order 4 have to be abelian because 4 is a prime squared, and fields of order prime squared are always abelian. And we know that this group is not cyclic because every one of these, when composed with itself, gives the identity. Just to convince you of that, take phi 1 for example. Suppose we compose phi 1 with itself. Then what happens to the basis elements? So I'm just going to record these down here. So these are my four basis elements. And then phi 1 maps these to 1, negative root 2, root 3, and negative root 6 respectively. If I apply phi 1 again, well, 1 still goes to 1, root 3 still goes to root 3, and then negative root 2, what is that going to go to? Well, that's going to go to negative the image of root 2. And root 2 we know goes to negative root 2, so that'll be negative root 2, which is just positive root 2. And then the same story for negative root 6. Negative root 6, after applying phi 1, will go to positive root 6. So we see here that composing phi 1 with itself gives an automorphism which takes every basis element to itself, which means it's really the identity automorphism. In other words, phi 1 composed with itself is the identity. And we could tell that same story for phi 2 and for phi 2 composed with phi 1. Okay, so this is not a cyclic group of order 4, it is the other abelian group of order 4, which is Z2 plus Z2. It's a direct product. Okay, one nice thing about knowing that is that we know what the subgroups of Z2 plus Z2 are. If we think of Z2 plus Z2 as the set of ordered pairs of elements of Z mod 2, that's 0, 0, 1, 0, 0, 1, and 1, 1. And each of those generates a subgroup of order 2, except for the identity, which just generates a subgroup of order 1. So I could look at the subgroup generated by 1, 0, subgroup generated by 0, 1, and the subgroup generated by 1, 1. Now I wasn't totally clear about which of these elements here corresponds to which automorphism up here. We could just go ahead and arbitrarily assign this to be phi 1. This is the identity, so it needs to be epsilon. Call this phi 2, and then this is phi 2 composed with phi 1, and that works out because 1, 1 is the sum of 1, 0 and 0, 1. So it's the composition of these two elements. Okay, so we have a nice analogous thing going on between these and these. All right, so I feel like analyzing the subgroup generated by phi1 would be kind of boring. Like we know what phi1 generates, just phi1 in the identity. I'd like to focus on this one. Okay, so this subgroup is also a subgroup of order 2. And that subgroup, in terms of automorphisms, it's epsilon and phi2, phi1. I want to ask, what is the fixed field of this? And you might be able to make a guess just by looking at this table over here and seeing what phi2, phi1 is doing. But I want to do this in a very careful way, just to show that we can actually work this entire question out using linear algebra. All right, so first of all, we know that the identity fixes everything. Nothing's going to change that. The identity fixes everything, so I really just need to pay attention to what gets fixed by phi2, phi1. All right, so first let's write down what phi2, phi1 does to a typical element of our field. A plus b root 2 plus c root 3 plus d root 6. Based on this table here, this is going to go to a plus b times negative root 2, so minus b root 2, and then plus c times negative root 3, that's minus c root 3, and then finally plus d root 6, because root 6 goes to itself. So we need to figure out for what combinations, or what values of a, b, c, and d is the domain element here, the input, equal to the output. So for what values of a, b, and c, and d are those equal? Okay, well, if we're trying to find out for what a, b, c, and d these are equal, we can go ahead and eliminate a and d root 6 because those are on both sides of my equation, and I can just get b plus root 2, or b root 2 plus c root 3. That needs to be equal to negative b root 2 minus c root 3. So in other words, for these to be equal, I need b root 2 and c root 3 to be equal to negative b root 2 minus c root 3. Okay, gathering up like terms, that means I need 2b root 2 plus 2c root 3. I need that all to equal 0. And I know that these are linearly independent over the rationals, which means for that to be equal to 0, I need both 2b and 2c to equal 0. So I need b equal to 0 and c equal to 0. That being said, a and d can be whatever I like. A and d can have any values whatsoever, and that won't interfere with this element being fixed. So it looks like the elements fixed by this phi2, phi1 are those of the form a plus d root 6, such that a and d are rational numbers. In other words, those elements in Q adjoin the square root of 6, which is another field that wasn't part of our lattice picture in the last video, but it nonetheless was in the background. If we're thinking about Q adjoin root 2 and root 3, there is an extension field Q adjoin root 6 lying inside of that. It's not the same extension field because this has degree 2 and Q adjoin root 2 and root 3 has degree 4 over the rationals, but this is a subfield of Q adjoin root 2 and root 3. So now we've surfaced another extension field of Q that is another field of, or rather a subfield of Q adjoin root 2 and root 3, and we did that just by taking a subgroup of this group, our group of automorphisms. So we took another subgroup and figured out what its fixed field was. All right, so now let's just put all this together. Okay, so big picture. So recall that we have our group of automorphisms of Q adjoin root 2 and root 3 over Q, that was Z2 plus Z2. There we go. And down here we have the trivial subgroup, just containing the identity element. Now, what other subgroups does Z2 plus Z2 have? Well, it has subgroups generated by 1, 0, 0, 1, and 1, 1. And those are all the subgroups because a subgroup of a group of order 4 has to have order 2 or 1, has to have order dividing 4. And these are the only subgroups of order 2 that there are. I just took any non-identity element and took the cyclic subgroup generated by it. Okay, so that is the lattice of subgroups of Z2 plus Z2. And in the meantime, down here, we have a lattice of fields. We have Q adjoin root 2 and root 3. We have Q down here. And then we have, well, we had Q adjoin root 2. And then Q adjoin root 3. So that's what we started with in the last video. Now let's think about the relationship between this lattice of subgroups and this lattice of subfields. Okay, let's think about what would happen if we took Z2 plus Z2, our entire group of automorphisms, and found the fixed field of that. What is the fixed field of all of these automorphisms? Well, now root 2 is no longer fixed because it's not fixed by phi1, and phi1 is in this group. Root 3 is no longer fixed, and root 6 is no longer fixed. The only things that are fixed by this entire group are the rationals. So I'm just going to mark that there. Okay, what about the subgroup generated by 1, 0? That is the subgroup generated by phi1. Well, if we look at our column for phi1 over in this table here on the left, what seems to be getting fixed? The root 3 is fixed, but root 2 and root 6 both move. So it looks like Q adjoin root 3 is the fixed field of that. And similarly, the fixed field of the subgroup generated by 0, 1, that is generated by phi2, that's going to be, there we go, it's going to be Q adjoin root 2. And then we actually worked out that the fixed field of this subgroup is Q adjoin root 6. That was the subgroup generated by phi2, phi1. Okay, what about the fixed field of just the identity automorphism? Well, that's going to be the entire field. Everything gets fixed by the identity. So the fixed field for that is going to be Q adjoin root 2 and root 3. So now this allows us to flesh out this picture down here. It's just the order is a little wacky, and also the orientation of the picture overall is a little bit strange. Because you'll notice that in this picture up here, the biggest subgroups seem to correspond to the smallest subfields, and conversely, the smallest subgroups have the largest fixed fields, because in the smaller subgroups, there are fewer automorphisms to move things around, which means more things are going to remain fixed. So the correspondence between the subgroup picture and the subfield picture, this is a deep theorem. It's called the fundamental theorem of Galois theory. And there's actually a little bit more to the fundamental theorem than that. But that's really the last big idea that I want you to walk away from the course with. And we will talk about that some more in what's to come.